$0.435 per million input tokens. That is for a 1.6 trillion parameter model running a native 1 million token context. The first time I saw it, I refreshed the page. I assumed it was a typo, or a decimal in the wrong place, or that someone on their pricing team had made a catastrophic mistake and was going to wake up the next morning, check Slack, and have a very bad day. It wasn't wrong. And the more I read about why they can charge that, the clearer it got that DeepSeek solved a problem most of the field had given up on solving cheaply. They got there with 2 attention mechanisms no other open source lab has deployed at this scale, a training approach most labs aren't experimenting with, and chips most labs don't use. So this video is about what DeepSeek V4 is, why the price isn't a mistake, and what it means for everyone else. I'll keep the technical parts readable, because I don't have a PhD either, and I still found this fascinating. Starting with what DeepSeek V4 is, and why the size matters, DeepSeek released V4 in late April 2026, alongside a 58-page technical report they published for free. We'll come back to the report, because it matters more than it sounds like it should. 2 models shipped, V4 Pro and V4 Flash. V4 Pro has 1.6 trillion total parameters, which makes it the largest open source model ever released. Since then, Moonshot AI released Kimi K3 in July 2026 at 2.8 trillion parameters, which now holds that record. But at V4's April launch, DeepSeek was out in front. Only 49 billion of those parameters are active at any moment during inference. That's the mixture of experts' architecture at work. The model is huge, but each task only wakes up a relevant slice of it. Flash does the same thing at smaller scale, 284 billion total parameters and 13 billion active. Both models run a native 1 million token context window, not a retrieval hack bolted on top. And then there's the pricing. The comparison I keep coming back to. The budget that runs Claude Opus 5 for 4 months runs V4 Pro for roughly 5 to 7 years. I've been in enough conversations about AI infrastructure costs to know there are only 2 explanations for a number like that. Either someone is burning enormous amounts of money to buy market share, which is the cynical read, or they changed something in the architecture and their cost structure is different now. Here, it's the architecture. To see why that's hard, you need to know why long context inference has always been expensive. About a year ago, I was building something that had to process long documents, research papers, and long reports. I loved the idea of dropping a whole document into a model and just asking it questions. First, 100K tokens, then 200K. The context windows kept growing and the marketing around them was getting confident. So I built the pipeline, fed in a long document, and started querying. The outputs were good. I was impressed, so I kept going. Then I looked at my API bill. The cost of long context inference at scale was, to put it gently, educational. It was the kind of bill where you sit quietly for a few minutes and reconsider some life choices. And I couldn't work out why. I thought bigger context windows were just a feature letting me do more. What I hadn't understood is that longer context doesn't use more memory in a straight line. It blows up compute. In standard attention, the mechanism transformers use to work out which parts of the input relate to each other, every token checks its relevance against every other token. The model isn't reading front to back. It's building a full map of relationships. At small scale, that's fine. At 1 million tokens, the map is enormous. Memory cost grows linearly with context length, and compute cost grows quadratically. At 1 million tokens, the model has 1 million memory slots, called the KV cache, and it scans them for every single token it generates. That's why most labs either cap context at 128K or price long context high enough that you only reach for it when you have no other option. DeepSeek's previous model, V3.2, had already made progress here with Sparse Attention, which cut how many memory entries get read per token, but the stored cache was still massive, reading less, storing everything. The memory side of the problem was untouched. V4 went after both sides, and the way they did it is clever. V4 introduced 2 new attention mechanisms, compressed sparse attention, or CSA, and heavily compressed attention, or HCA. Once you have both of them, the pricing stops looking strange. The core insight behind CSA is that most tokens don't need a permanent entry of their own. A few neighboring tokens usually carry one idea between them. So instead of keeping every token as its own entry in the KV cache, CSA compresses every 4 tokens into a single entry. The compression is learned, not a simple average. It isn't take 4 tokens, smush them together, hope for the best. Each token produces a candidate and a weight. a signal for how much it should contribute to the compressed group. So the model learns which information to preserve and which to let fade into the summary. Even at 4x compression, a million token cache is still large, so CSA adds a second step. A lightweight indexer scans the compressed memory and picks only the blocks most likely to matter for the current query. The model attends to those rather than to everything. That's CSA, compression, plus selective retrieval. Now, HCA pushes the same idea much further. Instead of 4 tokens into 1, it compresses every 128 tokens into a single entry, which makes it 32 times lighter than CSA. Because that memory is now so small, the model can attend to all of it densely. It looks at everything. What it gives up is precision. HCA isn't for pulling one specific fact out of deep inside a document. It gives the model a cheap read on the entire context, a one-page summary of everything it has seen. Think like this. If CSA is a search through the passages you highlighted, HCA is skimming the chapter summaries at the back of the book. Less precise, close to free. Both mechanisms also include a sliding window branch that keeps the 128 most recent tokens as completely normal, uncompressed entries. The tokens you just read are almost always the most relevant for predicting what comes next, so you don't want those compressed early. That leaves 3 timescales of memory running at once. Full uncompressed attention over the last 128 tokens, mid-range context through CSA blocks, long history through HCA summaries. Layers alternate between CSA and HCA across the whole model. The KV cache still grows with sequence length. This isn't a magical constant memory trick. The rate of growth is just dramatically slower. At 1 million tokens, V4 Pro uses about 10% of the KV cache v3.2 needed, and V4 Flash about 7%. Measured against GQA, the attention standard used in Llama 2 and Llama 3, V4 Pro's total cache reduction is roughly 34 times, and V4 Flash's is 49 times. 49 times less memory. I reread that line, assuming I'd misread it. I hadn't. Compute moved too. At 1 million context, V4 Pro needs only 27% of the single token inference flops v3.2 needed. Memory and compute drop together, and that's where $0.435 comes from. The attention work gets the headline, but a few other things in V4 are worth understanding. They moved most of the model's parameters onto the muon optimizer. Atom W, the standard basically everywhere, still handles embeddings and prediction heads, but muon took over the main weights. DeepSeek says it gave them faster convergence and better training stability, which mattered a lot, because training 1.6 trillion parameters with brand new attention mechanisms and a new residual architecture is not a relaxing experience. They also added MHC, manifold constrained hyperconnections, to the residual stream. Instead of information flowing through one path, it flows through multiple streams that get mixed before and after each layer. More representational capacity without a proportional compute overhead. The details are dense, but in practice, the model handles complex relationships better at scale, and they used FP4 quantization-aware training on the MOE expert weights. This one is subtle and easy to skip past. Normally, quantizing a model after training costs you quality because the weights were never trained to handle low precision. DeepSeek simulated FP4 behavior during training instead, so the weights learned to survive at extremely low precision. In a massive sparse MOE model, a huge portion of serving cost is moving and computing expert weights, so shrinking those to FP4 while keeping quality does an enormous amount of work on the final serving cost. All of this ran on Huawei Ascend 910C chips rather than NVIDIA. Export restrictions pushed them off the standard stack entirely, and most write-ups skip past the fact that they delivered this on non-NVIDIA hardware. The decision I'd want other labs to pay attention to is the post-training approach. Rather than applying reinforcement learning to the final model, which is how most labs do it, DeepSeek went back to the base checkpoint and trained separate specialists in parallel. One for math, one for coding, one for agent tasks, one for instruction following. Each got optimized for its own domain. The final model then learned from all of them at once through distillation. The reasoning is clean and obvious in hindsight. Mixing RL objectives across every domain in one model puts them in competition, with math reward signals pulling one direction and instruction following pulling another. Separate specialists plus distillation avoids that conflict, and the final model gets what each specialist learned without the interference. I'd seen this proposed in research, but hadn't seen anyone run it at this scale. It's the kind of decision that reads as obvious afterwards, and is apparently very difficult to execute. On the rankings, I want to be accurate rather than excited. V4 Pro Max is the strongest open weights model on most benchmarks right now. On long context tasks, it beat Gemini 3.1 Pro on academic benchmarks, and DeepSeek put the claim in the paper in those words, DeepSeek V4 Pro is better than Gemini 3.1 Pro. Academic papers don't usually talk like that. It got my attention. On overall rankings, Pro Max generally places second or third among open weights models, and it competes seriously with closed models that cost dramatically more to run. On reasoning, the hardest multi-step problem-solving benchmarks, it trails GPT 5.4 and Gemini 3.1 Pro. What I respect is that DeepSeek says so themselves. The paper puts the gap at roughly 3 to 6 months behind frontier closed models on reasoning. That's useful information, and it's honest, which is more than most labs give you. Most lab papers read like a marketing document that occasionally mentions a benchmark. DeepSeek's reads like they want you to understand the trade-offs. There's one small detail in the paper that says something about where the real demand is. When they benchmarked against Kimi K2.6 and GLM 5.1, some comparison entries are blank because those models' APIs were too overloaded to return responses during testing. Most of the coverage I've seen went to the benchmarks and the pricing. The part I think is underrated is Flash. V4 Flash, the smaller model at 13 billion active parameters, reportedly matches GPT 5.2 and Gemini 3.0 Pro on reasoning tasks when you give it a larger thinking budget. A small model punching that far above its weight class isn't only about architecture. Inference got cheap enough that you can just let it think longer on hard problems. That changes the equation for how you build AI applications. Usually let the model think longer is a luxury you save for your hardest, most critical queries, where the cost is justified. V4's cost structure makes it a default optimization strategy rather than a premium option. There are 3 reasoning modes built in: non-thinking for fast direct answers, think high for explicit reasoning before answering, and think max for maximum reasoning effort with longer context. When you see V4 Pro Max mentioned anywhere, that's V4 Pro running in think max mode. Same architecture, highest reasoning effort. It also points at a different competitive strategy from everyone else's. The rest of the field is racing on benchmark scores, chasing the highest number on the hardest eval. DeepSeek is racing on what it costs to run 1 million tokens, winning on cost compounds in a way that winning an eval does not. Now let's talk about why the 58-page report matters as much as the model. The 58-page technical report came out alongside V4 with all of it inside. The full architecture, the attention mechanism designs, the training details, the optimizer choices, the infrastructure decisions on Huawei chips. Most labs would file every bit of that under competitive advantage. DeepSeek published it. In a field where papers describe what a model can do while carefully omitting how a 58-page engineering spec released for free is a statement. Not charity, confidence. It says, we know something you don't, and even if you read exactly how we did it, you can't easily replicate it. They're probably right, and the field benefits anyway. Research groups will read it and build on it. Other labs will implement variants, and the ideas in CSA and HCA will show up in other architectures inside a year. Benchmark results age. Architectural ideas last longer, and that's what separates this release from a model that just scores well. So, a 1.6 trillion parameter model with 2 new attention mechanisms, 49 times less memory at 1 million tokens, a training approach most labs aren't using, running on non-NVIDIA hardware, a 75% permanent price cut, and a 58-page technical report explaining all of it for free. I refreshed that pricing page 3 times because I was sure something was wrong. Nothing was. They just did the work. If this helped you understand what's going on here rather than just hear the numbers, that's all I wanted. Hit like if it was useful, it does help the channel, and subscribe for more breakdowns like this. And drop a comment. Which part surprised you most? I'm curious whether it's the pricing, the attention mechanisms, or the Huawei chips. See you in the next one.